Good afternoon. Today we are presenting our work on image segmentation of biological cells. Regularization improves imbalanced multiclass segmentation. We'd like to thank the symposium organizers for accepting our work for presentation. My name is Cunha. We focus our work on the problem separating cells when they are together, bumping each other in clusters, as shown in these images. The challenge is not to separate cells from their background, which usually has a distinct appearance. The difficulty is on isolated adjacent touching cells, especially when the touching region has a signal distribution similar to the interior of the cell. This work is an improvement upon developments done in the last 2 years or so to build deep learning methods for segmentation of clustered cells. Our approaches over these years have mainly been in 4 areas. The first one is to create new loss functions that can lead to faster and correct optimization. Ideally, we would like to have a loss that can be optimized in a few epochs with high accuracy. The second area is on multiclass segmentation. We have shown in our 2018 work that adopting 3 classes for pixels, namely background, cell, and touching pixels, can lead to improved segmentations that could not be obtained if formulating the segmentation problem as a binary classification problem. In this present work, we add 1 more class, expanding the total number of pixel classes to 4. The third area has to do with treating pixel imbalance. As we all know from experience, if left unattended, pixel imbalance can lead to a poor classification. In our previous works, we use weights to balance pixel classes. These weights depend not only on the number of pixels per class, but they are also driven by cell shape. It seems to be easier to segment a convex cell than a highly non-convex one. We now have a more elegant strategy to deal with imbalance. And last but not least, we have devised a new scheme for data augmentation that modulates intensities of edges shared by adjacent cells. I will not be talking about augmentation today. This slide gives a general overview of our approach for segmentation, so I will spend some time here. We consider the problem of learning an instance segmentation of cells as a semantic segmentation task. We use ground truth cells to create semantic maps, and we then train a UNet with multiple classes. We have chosen UNet because it has been shown in the literature that it works well for small-sized datasets and for segmentation problems in general. The network produces an output, a probability map, for each class considered during the training. This is represented in this slide by variable z, each indexed for a specific class. In this particular case, we have 3 classes. Background is 0, cell is 1, and touching pixels are assigned class 2, as shown in the top right figures. The ground truth for each class is given right below those figures and represented by variable y, also indexed by class. The training loss, shown on the bottom right, is a weighted cross entropy. Weights are introduced to balance the training data. We no longer use weights. In 2018, we introduced the touching class as a third class to help segment adjacent cells. The output probability maps created by the network are thresholded using the parameters gamma 1 and gamma 2 shown here on this slide to create cell masks and touching masks. All pixels in these touching masks are then distributed to those closest cells, generating then the final instances representing the cells. We were not totally happy having to choose thresholds to create a final segmentation. We then, in 2019, moved to use watershed with markers to create a more automatic segmentation out of the probability maps. The seeds were automatically created by thresholding background and foreground probability maps at high values. The topographic map was created by taking the difference between touching and cell probability maps. The final instance segmentation is obtained by running the watershed with these seeds on the topographic map. We still had to threshold to create seeds, so not necessarily a bad alternative, but we wanted to move away from that choice. Results, though, were really improved. In the current work, we considered 4 classes for pixels: background, cell, touching, and the new class gap. The gap class was introduced to help in the classification of those narrow background regions between cells, which were until then classified as starting regions and then subsequently assigned to be part of cells. This was not correct. The network was not able to correctly classify the pixels in those regions as background. We think that might have happened due to the contraction of those small gaps during the max pooling, which were then not resolved well during the upsampling part of UNet. Adding the fourth gap class resolved the issue pretty well. We want to use maximum a posteriori decision rule to assign predicted classes to pixels. A weak prediction, maybe due to a weak signal, may lead to some confusion, mostly around junction points, as shown in this example. This can result in mistakenly merging adjacent cells into a single cell. Pixels at this junction should have been classified as touching so they can separate the adjacent cells. Watershed work well in these cases as shown in the plot. But maybe we can have a stronger classifier that can take care of those troubling regions. We have obtained a stronger classifier by adopting the J statistics introduced by William J. Uden in 1950, also known today as Uden index. In a binary classification, this index gives equal importance to the positive and negative classes. The index evaluates the ability of the classifier to avoid failure. It complements accuracy, which evaluates the overall effectiveness of the classifier with emphasis on the probability of the true value of the class label. And since cross entropy is the closest surrogate for accuracy, it makes sense for us to have both cross entropy and Uden index as a combined measure to evaluate classification. This is what we have done here. By combining cross entropy and Uden index, we believe we have created a stronger classifier for segmentation. We will see in the next slide that the Uden index naturally handles class imbalance, which is a much desired feature for segmentation. We most often have way too many background pixels when compared to the other types of pixels. In fact, the number of touching and gapped pixels is most often considerably lower than the number of cell and background pixels. Therefore, a measure that can intrinsically handle such balanced discrepancy is very welcome. Here in this slide, we show the expressions we use to compute the Uden index. The index is bound in the -1 to 1 interval. The higher the value of the index, the better is the classifier. So we want to maximize this index. A value of 1 is a perfect classification, no false positives or negatives. We can approximate true positive and true negative rates using the computed probability values, shown as z values here, and the ground truth probability shown as y values. These are surrogates that have already been used in other works. We just borrowed them. We can then define a binary surrogate for the index in terms of logarithm, as is shown by the top two expressions on the slide. Since this is a binary surrogate, we want to have not only two, but multiple classes. We need to expand the surrogate then to multiple classes. We do this by taking the sum of pairwise binary surrogates. We thus obtain the expression shown in the middle of the slide. Note that the regularization coefficient lambda is now taken pairwise, which indicates with indices I and k. These can accommodate different balances between classes if there is in fact a need for that. In our practice, we keep the regularization coefficients the same for all pairwise classes. We have used a value of 0.5 for lambda, which has worked pretty well. At the bottom of the slide, we find our new loss. We call it JC. J for the J statistics and C for the cross entropy. The first terms on the right side of the equation correspond to regular cross entropy. Nothing new here. Note that we no longer use weights in the cross entropy. With some algebraic manipulation, we can give the expression for the J component shown the double class summation. We have mentioned before that the J statistic is robust to class imbalance. We will show here in this slide. Here, We show plots of binary classification behavior of various loss surrogates commonly used in deep learning methods for image segmentation in our Uden index, all under different class imbalances. The value of pi in the plots implemented in 0-1 intervals gives the class imbalance. A value of 0.5 means there is no imbalance. Both classes contain the same number of samples. A value towards 0 suggests high imbalance. The lowest we went was 0.01, 1%, highly imbalanced classes. The score value on the y-axis tells us the ability of the measure to handle class imbalance. We want this to be flat 0. From all tested surrogates, only Uden and the Matthew correlation coefficient are invariant to class imbalance. The advantage of Uden over Matthew is the simplicity of its expression in terms of computation and understanding. The idea of using these random classifiers C1 and C3 to test predictions is not from us, it's from the literature. We run a simulation to show how combining J statistics and cross entropy work on tandem. The target segmentation are two touching squares with a 1 pixel wide gap between them, halfway their size. We start with a large proposal for the segmentation, shrink wrap it until it reaches the target segmentation. The plots of the loss on the left and its gradient on the right show how the two parts of the new JC loss behave. The green curve is for the combination, our new JC loss. The blue curve is for the cross entropy, and the red one for the Uden surrogate. When not working together, both cross entropy and J statistics stagnate. Only when combined, they produce the desired result. Observe the vanishing of the cross entropy gradient on the right plot. It stops contributing to the optimization after around 46 iterations, when the Uden takes over and starts driving the optimization. We show in this slide the shape of a new loss around an optimal configuration of the network. It shows deeper gradients which enable faster convergences during optimization. Even though if it is just a projection, it gives an idea how convex it is, or close to convex it is, our new loss. A few results on sparse and not so sparse clusters are shown on this slide. Our 4 classes approach produces better results at the end, which is shown in the 4th column. The same here for an average panoptic quality assessment of a pool of segmentations. Our 4 classes approach with Uden regularization produces results better than others, including when only 3 classes are used also with Uden regularization. 4 classes are better than 3. We present here on this slide some examples for different types of images and cell shapes. Again, note the benefits of using 4 classes instead of 3. It works much better to separate close by cells and capture small gaps. Here are some numbers showing the performance of the Uden regularization with 3 and 4 classes. Indeed, adding an extra class pays off, even for 3D images, shown on the Meyerowitz 3D rows in the table. We are proud of this example. We can segment this large image stack in a reasonable amount of time, especially when using 4 GPUs. The quality of the segmentation is assessed on a quasi-optimal ground truth, and thus it is an approximation, but it already shows the benefits of our developments for this type of problems. That's it for today. Thank you for your attention. I hope you and your families are healthy and safe in these difficult times.